let's talk about the integral test. So let's say that we have a series, this 1 over n squared, as n goes from 1 to infinity. So if I were to write out a few terms of that series, the first term would be 1 over 1 squared, and the second term would be 1 over 2 squared, and then 1 over 3 squared. We keep adding those terms. The general term, as we can see, is 1 over n squared, and it goes on forever. Okay. Now I want you to take a look at a picture, um, which is sitting just below here. So the first thing I want you to notice is that I'm taking this n and I'm replacing it with an x, and I'm graphing this curve y is equal to x squared, which is in blue right here. Okay. And then what I want to do is I want to take each term of this series, and this term can be represented with an area, which is this, in this case, it's a square. And then the next term, 1 over 2 squared, that can be represented with the second square over here. Or rather, this is a rectangle. And then, you know, we have subsequent rectangles represent the other terms. Now, when we look at this area comprised of all of these boxes, you can almost think of this as an area approximation. And if you look here, it looks like we're using right endpoint approximations. And I guess the key thing that I want you to notice is that the sum of the entries in this particular case, I'm saying the sum from as n goes from 1 to infinity of 1 over n squared. This is actually less than the area under the curve. Okay, now I'm going to draw a vertical line at 1 here in green. So you see that vertical line in green there. From this graph, we can see that this infinite sum, 1 over n squared, is actually going to be less than, so I'm going to put a little less than symbol here, 1 plus the integral from 1 to infinity of 1 over x squared dx. So just to be perfectly clear, the 1 is the square on the left side of the green line, and then this integral from 1 to infinity of 1 over x squared, that's the area from 1 to infinity. In other words, I want to avoid this vertical asymptote at x equal to 0. So I'm going to start my integral from x equal to 1, and then I'm just going to account for that first box by adding a 1 there. And because the area of the boxes on the right of the green line are under the curve, we know that this sum is going to be less than this expression on the right over here. Okay, cool. So let's take a look at a different graph now. In this particular case, I have a different infinite sum. I have this 1 over the square root of n, or 1 over n to the 1/2 power. Okay, and what I'm going to do now is I'm going to graph each of the terms. So just like before, I could write out a few terms. This would be 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3, and it just keeps going on. And what you could see by looking at the graph below is that each of these terms is going to correspond to a different blue rectangle in this graph. And what do you notice that's interesting about this particular graph? Well, what we notice is that the sum of the entries, summation as n goes from 1 to infinity of 1 over n to the 1/2, this is actually greater than the area under the curve. Okay. In other words, I could really write this as follows. I could say the integral from 1 to infinity of 1 over the square root of x dx. This is actually going to be less than the infinite sum as n goes from 1 to infinity of 1 over the square root of n, right? And then the natural question we could ask ourselves is, let's take a look at this piece right here, and we know how to calculate this integral, right? This integral is really, we could really write this as the integral from 1 to infinity, 1 over x to the 1/2 power. And if I take a look at this exponent, that exponent is 1/2. So, so really, this is an integral of the form 1 over x to the p as we go from 1 to infinity dx, where p is equal to 1/2. Now, from a previous example in section 7.8, we saw that when p is less than 1, our integral from 1 to infinity of 1 over x to the p dx diverges. So this basically tells us that our infinite sum from 1 to infinity of 1 over the square root of n diverges. Okay. Okay, so let's try to capture all of this in a theorem. This theorem is called the integral test, and the integral test has certain conditions that must be satisfied before we can use it. So we are going to need to suppose that our function f of x is continuous, positive, and decreasing. Okay, so if f of x is a continuous, positive, decreasing function on the interval from 1 to infinity, then what we can do is we can define a function that agrees with our series at each of those integers from 1, 2, 3, and so on. Okay, and our conclusion of our theorem is going to be the following. So there's kind of two cases. The first case is when this integral from 1 to infinity of f of x dx, if this integral converges, then this implies that our infinite sum, an, also converges. Okay, and this CGS is my shorthand notation for converges, and we're going to be using that pretty much all the time. On the other hand, if that integral from 1 to infinity of f of x dx, if this diverges, then this means that our infinite sum also diverges. Okay, so this is going to work for us as long as these three conditions, that f is continuous, f is positive, and f is decreasing. And we need our series, obviously, to agree with f, our function f to agree with the entries of the series at the positive integers. All right, everyone, we'll look at an example in class. Take care.